Yum. How many views do the videos get?
Some of them get more than others, you know, depending on the concept, but usually somewhere less than 10. All right. So, if you have not done so, hey, come on. If you have not done so, the outline from yesterday called Intro to Mechanics, make sure we grab that. We're going to pick it up from there today. So, like it says up on the board, all of our physics classes and physics units generally start with mechanics, and mechanics is the study of motion. And we talked about that if we're going to study motion and describe motion, there are 4 questions that we want to answer. So, what are the 4 questions that we want to answer? What's one of the 4 questions that we want to answer? Where is the object? That's one question. Okay, great. What is it doing right now? What's it going to do next, or what's it going to do in the future? And then, when? You can just yell at it. When are all these things happening? All right? So yesterday, we talked about the first question called, where is the object? And what do we call that description of where the object is? Position. The position of the object. But we discussed throughout the course of yesterday that sometimes describing the position can be a little bit tricky. So in order to accurately describe the position, we need to know 2 things. First, we have to define ourselves a reference point, and then after that, we have to define ourselves a directional system. The reference point and the directional system we call the frame of reference. Okay. There it is. So the frame of reference, the context in which we study motion. Basically, we're setting the ground rules for how we're going to answer all of those questions. Now, I had a question for you. Oh, so I remembered what it was. We're going to start our study of motion, and for the most part, keep it there, with what we refer to as one-dimensional motion. What does one dimension look like? A straight line. Okay? That being said, we only have 2 choices on a straight line, right? Which way can we go? That way or that way, right? And so yesterday, we set ourselves up a frame of reference that looked a lot like a number line. So on a number line, what is our reference point? 0. And then how do we tell one direction from the other? Positive, negative. All right? So that's our frame of reference when we're talking about a one-dimensional motion. So the position is where an object is relative to the reference point. And that's great until the object moves, right? So, describing the motion of the object, we talked about what term do we use to describe the motion or the change in the position of an object. Displacement. In order to calculate the displacement, in order to determine the displacement, you need to know 2 things. You guys want to let Ronnie answer it, or does somebody else want to answer it? No. No. In order to determine the displacement, what do you need to know? Where it starts and where it ends. Okay? That's how we determine the displacement. Where does it start and where does it end? So we use the top equation to calculate the displacement, right? Delta x is equal to x final minus x initial. What do we say the delta represents? Change. So if it's delta x, it's change along the x-axis. Okay? That's how we determine the displacement. But then we got into the idea that we have this displacement, but we could also have this displacement. what's the obvious difference between those two displacements? Well, what's the difference? When we look at it, what do we see differently?
It's going the opposite.
Opposite direction. How do we distinguish the opposite direction?
Turn the
How do we
Scissors
show?
around.
No. How do we show the opposite direction if we're describing the displacement? We can show arrows. How would we describe it from the number?
Negative.
Positive versus negative, right? That's where we get into the directional system. So, displacement not only has to tell us how far we went, but it also has to tell us which way you went. And that means that displacement is an example, Ronnie, of what we call a... If it tells us how far and which way, it's a vector quantity, right? So, vector quantities have to tell us, magnitude and direction. How much in which way? So displacement tells us not only how far we went, but also which way we went. Important point to remember as we go forward with this. Here's a negative 66 displacement. Here is a positive 61 displacement. Which displacement is bigger? Negative 66 is bigger than positive 61. The positive sign and the negative sign doesn't tell us anything about how big something is. It only tells us which direction. Okay? Keep that in mind as we go forward because we're going to run into more vector quantities later today. Okay? Good with this so far?
Yes.
All right. At the end of class yesterday, we talked about this poor guy and his trip, right? And we talked about that his displacement when he runs out of gas is 50 kilometers to the east because we have to include both a magnitude and a direction. How far and which way, right? That his displacement when he arrives at the gas station is 55 kilometers east. But then when the stranger picks him up, his displacement is only 52 kilometers east because he started going back and he's closer to his reference point than he was at the gas station. But then, eventually, where does he end up? At his house. Or, Dublin, if we talk about defining displacements, right where he started, right? So if you need to know starting point and ending point to calculate displacement, if your starting point and your ending point are the same, what is your overall displacement? 0. But sometimes that doesn't tell us the whole story. If we say that this guy's displacement was 0, does that accurately describe the hardship that he went through that day? Not really, right? So sometimes just knowing the starting point and the ending point isn't enough to describe what happened. And that's where we get into our next description, our next quantity, right? Where...
For the last one,
Yep.
what if the next displacement is a type short?
Yep.
When you put 0, would you put the E afterwards?
No, because there's only one place that he can end up for the displacement to be 0, and that's right back where he started. So there isn't 0 east or 0 west or 0 north or 0 south. It's just 0. Okay. Yeah, that's one time when you don't have to put the direction because there's only one place that he could have ended up to make that 0 displacement. All right. Displacement is the change in position. And sometimes that's great, but sometimes it's not descriptive enough. So sometimes we have to rely on the distance traveled. Distance traveled is the length of the total trip that we've taken between a starting point and an ending point. All right.
Mine is in a packet.
Check and see if there's an extra packet back there. If not, I'll give you the originals. Go back on the blue tray and see if there's an extra. All right, so distance traveled is an example of a scalar quantity. Vector quantities have to tell you two things. They have to tell you magnitude and direction. Scalar quantities only tell you one thing. They only tell you magnitude. And we said magnitude is a fancy way of saying what? Not which way.
How much.
How much, right? Or how big or how far. Okay? So, let me relay a story to you, an example. Hopefully this example is in your future. Okay? So let's say a year from now, a year and a half from now, maybe 2 years from now, your parents decide that they're going to get you a car. Okay? I know, I'm just saying, hopefully it's in your future, maybe it's not, but, you know. So let's say your parents get you a car, okay, or going to get you a car. So you go to the dealership, and you find a brand new car, right? They're not even just going to give you a used car, like a brand new one, all right? I know. Damn is right. All right, now, let's say, for the sake of argument, and I know this never happens when you buy, like, do you need?
Do you know where a stapler is? Oh, thanks.
Let's say for the sake of argument, and I know that this doesn't happen, but let's say when you get the car at the lot, right, you get into it, and the little odometer thing there says 0 miles, brand new. I know that doesn't happen, but let's say that it does. So you get your car, you drive it back and forth to school every day during senior year, then you get to take it to college, so you drive to college, you drive it for 4 years when you're at college, you come home on break, blah, blah, blah. Then you graduate college, you get a job, you start driving it to your new job, and let's say after 6 or 7 years, you're like, okay, I got to get a new car. And as what happens a lot with people that are in their early 20s, you generally do things the way that your parents did them, just because that's what you know. So you go right back to the same dealership that you originally got your car from. Okay? 7 years later. What's the displacement of that car?
0.
0. But does that mean you're going to get the same money back when you trade in your car that you paid for it? No. Displacement doesn't tell the story of that car, right? We need to take a look at not just where the car ended up eventually, but what exciting trips it went on during that time, right? So, distance traveled tells you the length of the path without regard for which way you went. It only tells you magnitude, it doesn't tell you direction. Okay? Does that make sense, at least for starters?
Yeah.
Okay. So with that being said, okay, everybody got that written down? Good? So with that being said, let's re-examine this situation of the guy and his trip. So, what is his distance traveled when his car runs out of gas? Okay, now, Devlin said 50 kilometers east. 50 kilometers, right? It doesn't matter which way he went. When we're talking about distance traveled, we only want to know how far. Okay? So then the next question, what's his distance traveled on the way to the gas station? If you can't remember the story, it's on the bottom of the first page, right? How far is it from where his car runs out of gas to the gas station? So 55 kilometers would be his distance traveled to get to the gas station. This is an extra 5 kilometers from where his car ran out of gas to the gas station. Now, in the last problem, this is where our answer changed, right? How far does he walk until the stranger picks him up? Well, he walks an extra how many? 3 kilometers. But if we're talking about distance traveled, does it matter that he's now going west when he was going east? No. So his distance traveled now is 58 kilometers. It doesn't matter that he's going back towards his starting points. Okay? And then that means that the total length of his trip on this day was what? 110 kilometers. It doesn't matter that half of them were in one direction and half of them are in the other direction. This more accurately describes, at least in terms of this story, what this guy went through his whole trip. He actually traveled 110 kilometers. It just so happens that in the course of traveling 110 kilometers, he ended up right back where he started. Ronnie, go ahead. So, here, right up at the top, right? Distance and displacement. Distance only tells you what? How far. Doesn't matter which way you go, it just matters how far you went. But displacement describes what? You want some help? How much, but also where they are. Yeah. Well, it's 55 when he drives the first 50, runs out of gas, and then walks 5 miles or 5 kilometers to get to the gas station. He did the first 50 in his car, then the next 5 on foot, but it's still 55. And then he turns around and starts walking back towards his house. He walks 3 kilometers, but when we're talking about distance, it doesn't matter which way you're walking, we just keep adding up how far you went. Does that make sense? So, right. A real good example of distance versus displacement is running around a track, right? If you run the 400 meters, right, the distance you traveled is what? 400 meters. But what's your displacement? Especially if you're in lane 1. 0, because you end up right back where you started. Does that make sense? Half of the time you're running in one direction, half the time you're running in the other direction. I know that's not exactly right because it's a circle, right? But half the time you're running one way, half the time you're running the other way. So in the end, it all sort of cancels out, and you end up right back where you started, but you actually ran 400 meters. Distance tells the whole story there, but sometimes we don't care about what happened in between, right? Sometimes we only need to know where it started and where it finished, right? So it depends on what you want to know. Okay? All right. Is that good? Okay. So, 4 questions, right? First question, where is the object? Second question is what? What is the object doing? Right? And again, depending on what we want to know, we could have some different answers to this question. So let's start with this one, speed. I'm assuming most of you are familiar with speed, right? We've heard of it before, yes? Okay? Speed is a derived quantity, meaning that we need to measure 2 things to describe the speed. What do we got to measure? No.
Oh, wait. Oh, no.
Distance and time, right? Speed is the rate at which distance is traveled. All right, so I'm going to try to do some preventative measures here so we don't have to go back and like review things, okay? So pay attention. Because in the last class, I went through like 3 slides, and then I said, hey, give me an honest answer. Do you understand what we talked about in the last 3 slides? And 3/4 of the people were like, nope, just wrote it down because it was on the board. So let's try and prevent that from happening here, okay? No. Totally something different. Okay? So, all right. So, pay attention. Remember, vocab. All right? So, we have discussed rates before. Whenever we describe something as a rate, we are measuring it over what? Time. All right? So a rate is a ratio. It's a ratio between something and time. In this case, speed is a ratio of distance to time. Okay? Good so far. So, speed is a rate, and any time that we describe something as a rate, we measure something over time. In this case, we're measuring distance over time. It's a ratio. Mathematically, how do we represent ratios? With a fraction. So, speed we can represent with a fraction. Where does time go in our fraction? On the bottom, because it's over time. In this case, what goes on the top of our fraction? Distance. So speed is equal to distance over time. What do we measure distance in? Meters. What do we measure time in? Seconds. So, to combine those units, we just go meters over seconds. Don't pay attention to the green stuff written on the side. That's for later. Okay. Here, I'll erase it so we know. Okay. So, speed is a derived quantity. We have to measure two things to describe speed. Distance and time. Okay? Good there? Alright, so here's a picture of a girl running a race. And we have a little stopwatch that's measuring 6 seconds worth of time. How far did she go in that 6 seconds? 50 meters. So to describe her, or to calculate her speed, what would you do? 50 divided by 6. And when you do it, you should get 8.333 repeating. Okay? Does that make sense? For starters. Okay so far? Okay. Now, here's where, right? Vocab. Remember our vocab, right? So, what do we know, what did we learn today about distance? Two things. Measured in meters, so it's how far you went, but something else maybe more importantly for this discussion. Go ahead, Rachel. It only indicates the length or the distance, and so we call it a what? A scalar quantity. Time. Is there any direction on time? Time's just a number, right? So if you have a scalar quantity in distance divided by a scalar quantity in time, speed is also going to be a scalar quantity. That means, what does speed describe for us? Go regular person words. If we talk about the speed of something. How fast it's going. But what does speed not tell us? The direction. Speed is a scalar quantity. It only tells us direction. But it only tells us magnitude, how fast something is going. But sometimes we need to know the direction, right? If we're trying to answer the question of what is the object doing now, sometimes which direction it's going is important. That's where this comes in. Average velocity. Okay? Speed and velocity may sound similar and you may use them interchangeably, but they are not the same. Average velocity. All right, everybody, it's connection time. All right? Get those brains moving. Okay? Ready? Here we go. average velocity is the rate of displacement of an object. Okay? Good for starters. Now, let's go to the next line on your outline, right? It says a ratio of the blank and the blank. Okay? What did we say that rate compared something over? Time. In this case, what are we comparing over time? Not distance. Displacement. Right? Distance and displacement are two different things. So it's a ratio of the displacement and the time. Those sound similar to what you just wrote down right above it on your outline, but it's not. It's a ratio between displacement and time. All right, get those brains moving, okay? Mathematically, how do we represent ratios? Fractions. What's going on the bottom of this fraction? Time. Displacement on the top. What notation did we use to represent displacement yesterday? What's the triangle called? Except it's not delta t, it's delta what? Delta x, because it's a change on the x-axis. So velocity is delta x over t. So velocity is displacement over time.
Please pardon the interruption. This is a PA test for the D-wing. A PA test for the D-wing. Thank you.
It's just social stuff. We're in C. All right, so what do we measure displacement in? Meters, right? It's still how far, right? And then we measure time in seconds. So velocity is also meters per second. Right? Good so far. Okay. Brain's working. What's the difference between distance and displacement? Give me one word that would describe the difference between distance and displacement. Direction. Right? So, direction is the only difference between distance and displacement. So that means, what's the difference between speed and velocity? Direction is the only difference. Velocity is a vector quantity. What do vector quantities have to tell us? Magnitude and direction. Now, in the case of velocity, the direction describes which way it's going. What is the magnitude going to tell you? The magnitude of velocity, how fast or speed. Okay? Velocity is a vector quantity. This is at the top of the next page. All right? Velocity tells us not only how fast it's going, but which way it's going. Also, which way it's going. We sometimes describe speed as the magnitude of velocity. Because what does magnitude tell us? How fast or how much, right? In the case of speed and velocity, how fast are we going? It doesn't matter which way you're going for speed, it does for velocity. So the little dial in a car, right behind the steering wheel, it's called the speedometer, right? Because what does it describe about the car? Speed. It describes how fast, right? But it doesn't describe what?
The direction.
Doesn't describe which way.
Compass form.
All right, are we okay with this? Are we good there? That's a vocab exercise, right? We need to know the difference between all those terms. So, here's our lizard friend again. We already calculated his displacements. I added a couple of stopwatches on there so we could find out the time. But more importantly, if we were calculating velocities here, what would we see about this velocity on the top versus this velocity on the bottom? One would be positive, one would be negative, because that's how we tell the difference in direction. Okay? First one's 20.75. No, 15.75. 15.25, crud. Positive 15.25. The bottom one is negative 20, something like that. All right, good there? Do you want me to do it real quick? Sure. All right, let's do this real quick. All right, so here is these two lizard pictures, okay? Jafar, the pictures are exactly the same in the front page, okay? So on the front page, we found out that his displacement here was positive 61 centimeters, okay? And the displacement for this picture was negative 66 centimeters. Does that make sense? Okay. So, we just learned that velocity, how do we calculate the velocity of something? Nope. How do we calculate the velocity? Displacement over time, right? So, we can take positive 61, and then based on our stopwatches here, Jafar, how long? 4 seconds, right? So we'll take positive 61 divided by 4 seconds, and we'll get 15.25, and then what's the unit going to be on this, Jafar? Meters per second. Okay. What is this distance measured in? Centimeters per second. So this isn't an SI unit, but it is a distance over time. Okay? Does that make sense? All right. Then down here, right? Oh, sorry, one more thing. Even though generally speaking, Jafar, we can kind of assume if we don't write anything, we can assume it's positive. We should get in the habit of doing. Okay? All right. Down here, negative 66 centimeters. How long, according to these stopwatches, did it take? 3 seconds. So that's negative 22 centimeters per second. Question. Sorry, finish writing that down. You tell me, can it be negative? So, that's a good question, right? So, Mehdi, what is this asking you to calculate? The average velocity. Velocity is a vector quantity. It has to tell us two things, right? What does it have to tell us? how fast and which way. If we're in one dimension, how do we tell this way from the other way? One's positive, one's negative. So can it be negative? Yes. Actually, in this case, it has to be negative because what did we call this one?
Positive.
This one's positive and it's going this way, but that means if this one's going this way, it has to be negative. Okay? Now, next question. Which one's faster, red or blue? Blue is faster even though it's a negative number, because the negative only tells us what? Which way. It only tells us direction. Does that make sense? Okay? So, can it be negative? Yes. It only tells, that's how we distinguish this way from that one. Okay? Because we don't know whether this is east or west, because it didn't give us that, but we do know that this lizard picture is going one way, and this lizard picture is going the other way, so we got to tell the difference between them. Okay? All right, good job today, everybody. We'll pick it up from there tomorrow. We'll start the lab up. We'll save acceleration until next week.